All right. So
Hey, am I just Sumit this side? I'm sorry, I was speaking one minute.
yes.
Because it is in one direction, can't you have the path as V1, V4, and V3? Or would it
Yeah,
only be
there is no
V1,
path
V2, and
here.
V3?
In this case, there is no path between V1, V4, and V3 like that, because this is one
Okay.
direction.
Had it been a multi-directional, it could have been V3, V4, and sorry, V1, V4, and V3.
No, it cannot be V1, V4, and you cannot go from V1 to V4 because the path is this way.
No, I'm saying that if it would be a multi-directional path, multi-directional edge, in that case, it could have been V1, V4, and V3,
Yeah, that is
hypothetically.
true. So let's say if just remove
Okay.
this, and let's make this way. Or you can have both way connecting like this,
Hmm.
however you want. So if you have this, then yeah, there are two paths, V1, V2,
Okay.
V3,
Got it.
V1, V4. And the question may be to find the shortest path between the two. And if this is the distance, then the length of this path is 3 and 6, which is 9. And the lower one is 6. So that would be the shortest path in that case.
Got it. Thank you.
Right? So that is basically the basic terminology of graph. Any other question? Okay. And we're going to come to writing some stuff pretty soon. Let's just quickly talk about the representation of graph. How are graphs represented in your programs? Suppose you take this graph again, okay? Suppose you have this graph like this, assume this, and I'm just numbering the nodes, 1, 2, 3, 4, and 5, like this. And suppose, once again, you have this. Suppose this type of situation. Then how can you represent this graph? There are two common ways of representing the graphs. One is the way of matrix, and the other is the way of adjacency list. Let's look at both of them. So a matrix essentially is a two-dimensional structure. What you will have here is all the vertices, 1, 2, 3, 4, 5, and then 1, 2, 3, 4, 5, like this. And if you have an edge between, if you don't have an edge between the two vertices, then this will be 0. There is nothing here, or minus infinity, or whatever you want. So 0. And then if there is something between 1 and 2, yes, then there's 1. That 1 means that there is something. If there is a weight and you want to keep weight here, that's fine too. But essentially it's like this. Then there is nothing between 1, 3, nothing between, or there's something between 1, 4, and then nothing between 1, 5. Similarly, let me use a different color actually. So 0, 1, 0, 1, 0, 1, 0, 1, 0, and then nothing between 2, 1. So basically, essentially 2 to 3, we have one edge. Then we have 4 to 3, one edge. And then we have 1 to 5, another edge. And 1 to 4, another edge. So we have 1 to 4, another edge. So that's covered. So that's pretty much 1, 2, 3, 4, 5. 1, 2, 3, 4. What is the remaining edge? 1, 2, 5. So 1, 2, 5, that edge right there. So essentially everything is 0. And that is an adjacency matrix. So you're given a 2D matrix in which both the dimensions are vertices. And if a value is 1, then essentially you have an edge between the two vertices. Otherwise, there is no edge between the two vertices. All right, so this method of representation is simple, but it tends to be inefficient in terms of space. Because you can see it's a very sparse type of matrix that most of the values are 0 and only very few values are 1. So it wastes a lot of space. If you have a graph which is very edge heavy, that is, there are a lot of edges. You have edges of all type coming here, like this, and then this, maybe more edges, then you can have, then this might still be efficient. Otherwise, this tend to be more inefficient. The other way of representing graph is an adjacency list. Adjacency list essentially in your computer programs will be represented as a hash map. Or in talking terms of Python, it will be dictionary. So what is an adjacency list in this case? So you'll have a graph data type, which essentially is a hash map. The key is going to be the vertex that you're talking about. For example, in this case, let's say 1. And the value of that would be a list of the neighbors. So in this case, the neighbors are 2, 5, and 4. So that's why, hence adjacency list, right? So this is a list of all the adjacent members for this vertex here. So this is, let's say 1, 2, 5, 4. For 2, you have one member, 3. For 3, you have nothing. For 4, you have 3. And for 5, you have nothing. Sorry. So based on how many edges are there, this requires exactly the same amount of space that you're going to need. So this tends to be more space efficient. And pretty much all the problems that we're going to look at, this is going to be how it's going to be represented. Just give me a second. You can take a quick screenshot of this. And once again, this is going to be the way that is going to be used most in all the programs. And this is just for the information, most likely not used. Right? That's the representation part, adjacency list. I'm going to code on all the problems using the adjacency list. Any questions?
Himanshu, Sumit, one second.
Yeah.
So what I understand is that it depends upon the direction of the edge that the matrix or the adjacency list would be there, right?
Right.
So because we are directing from 1 to 2, that's why in the matrix we did not put any place for 1, where the row is 2 and the column is 1, right?
Yes.
Okay.
Because
So
this is
the second
directed
part
in
of-
nature. This is directed graph in nature. So you have 1 to 2.
Okay.
There is no 2
Now,
to.
my question.
If this was an undirected
Okay.
graph, then you would put 1 here as well.
Got it. My question is basically related to adjacency list, that if I see 1 is in the key as a dictionary, and let's say I see 2 in the value, so that means I am directing from 1 to 2, because there was no 1 in the second point of dictionary, that is 2. That's why I understand that it is unidirectional edge.
So if you had if this was an undirected graph, then you will have something like this as well. So you would have 2 connecting to both 3 and 1.
And 1.
Like
Got it.
that.
Thank you.
Any other questions?
I have a question.
Yeah.
I wonder, could you show in the picture before that for example, between 1 and 2, they might have a distance. Let's say from 1 to 2 is 3. How can you implement that in matrix and the hash map?
So I will talk about that. Just hold that question for a while. Okay, we're going to talk about a problem in which we're going to calculate the distance, and we'll talk about that as well.
Okay, thank you.
Yeah. All right. So let's look at So we have talked about what graphs are, some terminology on graph, some representation, like how you can represent stuff in in your program, how you represent a graph in your program. All right. So now let's come to the implementation of some important algorithms. So first is, how do you traverse a graph? Okay, when you will model a graph, there is a real world situation that is going to be modeled into a graph. And surprisingly, many a time, what will happen is the problem that is given will not explicitly say graph, but you will have to construct a graph in order to solve that problem. And we will look at some of those. But in order to essentially solve any problem on graph, you have to go through all the vertices of the graph. So traversal is one of the important part of graphs, and pretty much every algorithm will require us to traverse the graph. Okay, and I'm going to talk about those traversals now. And my objective for today is to get through all these traversals, and then continue with problems in the second session. So there are two main type of traversals. Okay, we're going to look both of them in great detail. So one is called BFS, this is called breadth first search, and the another one is called DFS, which is depth first search. Right. So breadth first search essentially means that explore the neighbors, then explore further depth. Depth first search essentially means that go down the depth along the one neighbor, and then once it's done, go the other path. And don't worry about it, I'm going to explain it now. This is implemented iteratively. This is implemented recursively and iteratively. Both. Recursive is more intuitive, but iterative is pretty simple too. There's no big deal. And this is implemented iteratively. You can implement recursive as well, but I mean, there is no sense to do that. Right? And with recursive, there is one important thing I will tell you, that it's very important, very good in finding, especially in problems in which you have to find cycles in graph. Okay. So with that, let's look at the breadth first search on our example number 1. Okay, let me create a graph real quick. So let's create a graph. Let's say you have A, B, C, E, F, and you have edges. Let's make sure that we don't have any cycles in this one. So let's say this goes like this goes like this goes like this goes like this. All right, and let's add one couple more edges. Okay, suppose you have X and Y, and this goes here and this goes here, suppose like that. So at the moment there are no cycles. So if from A, for example, you cannot come back to A. You can go A, B, and you can go E here. But this is a directed edge, you cannot go back here. So there is no cycle essentially in this graph at the moment. So let's explore the traversals. Now BFS, if two people implement BFS, you can still get different answers based on how you're prioritizing. But so don't worry about if you get different answers while doing BFS. Okay, but essentially what BFS says is this, that if you start breadth first search, BFS is breadth first search, if you start that, then essentially first you explore neighbors, NBRs. I'm going to write NBR as neighbors. So if you explore, if you start breadth first search on any node, first you will explore all the neighbors of that node. Then you will explore the neighbors of that node. And in that way, you will move forward. Right? So let's say if you want to write the BFS of this graph, starting with X. Okay, so all the nodes are there. We have to visit all the nodes. So let's say with A, if we begin, then what are the neighbors of A in this case? We have two neighbors, B and D. Those are the two neighbors. So the next in the listing would be B and D, like that. Now we have to explore the neighbors of both B and D. Now A is done. A had two neighbors and both of them have been listed. So now the next one is B. We have to find out who are the neighbors of B. So the neighbors of B is E. Okay, and sorry, let's just back this a bit. So then B has two neighbors, D and E. D is already listed here, all right? So we don't need to do anything. So the next neighbor is E. And after that, B is done. There is nothing left in B. Then the next node that we need to explore is D. So who are the neighbors of D? E. But E is already there, so nothing needs to be done. That's the only neighbor D has. And D is finished. Then the next node is E. E has one neighbor, F. After that, E has no neighbors, so E is done. F has two neighbors, C and Y. After that, F is done. And then C has no neighbors, finish. Y has one neighbor, X. And that is it. X has no neighbors. So that's the breadth first search traversal of this graph. So we explore the neighbors. So we are given, so for example, if you write an algorithm, you will be given a graph, G, and you will be given a node, or you can call it a vertex, let's say V. And in this graph, starting with V, you have to do the breadth first search. Any questions?
So in a tree, actually, we start with the root node, right?
Right.
And what about in graph?
In graphs, you might be asked to start at any node.
Okay.
Right. And so for example, let's say if it's a graph of all the cities, connected cities, then essentially you may be asked to start from one particular city, and then you may be going in that direction. So you have to do a breadth first search from that particular node. Now there are some details that I'm skipping at the moment. I'll cover later as we move forward. And these algorithms as well, I'm going to develop over time. So I'm going to write a very basic one, which is going to fail, and then I'm going to add more complexity to it, and then it will start working.
Himanshu Sumit again. So can you please share some real life examples for both tree and this other one?
What I did not get the question. Can you repeat again?
Some real life examples where one should be using tree as a graph, and other one where should be using the other option.
One should be using tree as a graph.
I'm saying so right now, the one which is shared on the screen here, you gave an example of finding out the distance between two cities. So either you can start off with B and then you can go to E, things like that. But could there be any example where you have to utilize the tree where the parent and child function is there? I mean, back of my head, I can think of continents and then countries inside it. So it would be in tree diagram, right?
So just hang on. So let me just do something. Okay, just give me 1 second. Okay, let me just first save this. Let's just call this BFS. So let's save this image. And let's get rid of this. Now, suppose you have a tree. Okay, and let's say the tree is something like this: A, B, C, D, E, and F. So tree also has a graph. Tree is also a graph of some sort. And one thing that I discussed in the tree was something called a level order traversal. Right, so suppose that in the tree you want to do a BFS. So suppose you want to call BFS on A in this tree. Then essentially what that would mean is that A, and then all its neighbor will be explored, BC. Then all the neighbor of B will be explored, DE, and then the neighbor of C will be explored, F. So if you notice, this is essentially the level order traversal. So whatever algorithms you have in graphs, you will be able to apply them on tree. Tree is much more simpler case compared to a graph, which can have loops and cycles and that kind of thing. Now, in terms of presenting, let's say a real life example. So suppose you have the same graph, what I created can be modeled into, let's say, cities, right? So you can have SF, you can have LA here. Let's say you have Sacramento, you can have Santa Cruz, and like that, right? You can have Fresno, like that. So in that way, you can model it like this, right? The same nodes. And then essentially this can be like, what is the route if you want to go to, let's say, Fresno from SF? So then you have this route and you have two routes. You can go like this. So essentially, I mean, this is like the practical example of it, if that's what you're looking for.
Yeah, thank you very much.
One thing to understand is, let's open this. Let's get back here and when you create, sometimes people talk about a term called Bfs tree. So when you run Bfs, essentially the result is a tree, not a real tree, but essentially the search is done like a tree. So suppose you start with A, then A has two neighbors, B, C. Then B has two neighbors, let's say, sorry, my mistake. A has two neighbors, B and D. Then B has one more neighbor, let's say E, and B has, just give me a second. Just give me 1 second. My computer is kind of acting up. Just give me guys 1 second. All right. Can you guys see my cursor moving?
Yes.
Okay, perfect. Okay, so yeah. Okay, so A has two neighbors, B and D, and then B has neighbor E. And then basically you have B connecting to F, and then F connecting to C and Y, and then Y connecting to X. So essentially this thing that is generated is called a Bfs tree. It's like a tree, like a structure in which you have a node, and then you list all the neighbors as its children, and then basically you need to list all the children of that node further, and then that creates a tree kind of a structure. That's Bfs tree. So there's nothing special about it. It's just, I just wanted to make sure that you know this term, Bfs tree. Similarly, you will have a Dfs tree as well later on. All right, so let's get down to implementing these things. How do we implement a BFS?
I have a question.
Yes.
I'm sorry, you just raised the BFS tree. When you had the BFS tree, the B has two neighbors. B has D and E. But in the tree, B only has E. So how do you represent that?
So once you have found a node, you don't explore it again. So if D has been listed, then you're done at that point.
Okay.
You will not list it again.
Okay.
Yeah, so B has D as a neighbor, but D is already there. So it's no more needed to be listed.
Okay.
Yeah.
Okay, got it. Thanks.
If you chose like a different order, assume that you chose a different order of exploration. All right. So let's say this is one tree. And if you chose a different order of exploration, then essentially you could have resulted in a different answer as well. You could have gotten into a different answer as well. Suppose you said the neighbors are D and B. There is no order in which you can choose, So you can then begin from D. So D has neighbors, let's say E, and then F, which then to C and Y, and then Y is X. you see these two trees, they're both BFS, but it's just we chose to explore B first versus in this case, we chose to explore D first. So BFS can give you different answers based on whatever you want to choose. But the concept remains same. We explore neighbors first, then neighbors of the neighbors. Let's look at DFS. And then we will come to the coding part of this. If we want to run DFS exploration on this particular graph, same graph, then what DFS would say is that you start with a node, let's say A. Then explore all the path, all the way it takes you to the point that it takes you. So let's say A, what are the neighbors of A? The neighbors of A are B and D. But what is the first neighbor of A? Let's assume that we call the first neighbor of A as B. It can be D as well, depends on whichever way you want to code. But let's say I say that the next neighbor is B. Okay, and then D is somewhere kept in the memory that it will be explored later on. Then what are the neighbors of B? Let's say E and D, but D is later on to be explored, right? And then what are the neighbors of E? F. Then what are the neighbors of F? C and Y. Let's just choose C and Y to be explored later. Then C is nothing. I mean, there is nothing left in C. So the next thing that is going to be explored is Y. Not D, Y, the last one. Y. And then what are the neighbors of Y? X. Once that whole path is explored, what is remaining is D. So let's explore D here, like that. That's the DFS. So you go the path from A to B to F, C. You did not find anything. Then you came here, did this, and then you jump to this next neighbor. And so you go to the depth along one path till you have explored everything. And then you come to the next path. Suppose this graph had more stuff in it. Right? Suppose it has I and then J like that. Then you would go D, I, and J. That would be a different path. So that's the difference between breadth first search and depth first search. Okay, let's solidify this once more on a simple graph that I initially wrote. Suppose this is the graph. A, B, C, D, and let's say E. Let's write the breadth first search real quick for this one. Breadth first search starting with node A. Okay, if I want to do that, then first thing I want to explore is node A itself. Then I want to explore all of its neighbors. Can anybody tell me what it should be?
BED.
Correct. So there should be B, E, and D. So A is explored. Now what should I explore next?
C.
B, right? So what are the neighbors of B? C, right? So now B is done. And we come to E. There are no neighbors of E. Done. D has a one neighbor. C. C is already explored. Done. There are no neighbors of C. That's the BFS. Let's do DFS on this. So suppose the first node is A. Then the next node, what should I write here?
E.
I can go along any of these paths, but let's just choose path B. All right, then what should I do?
C.
C.
C, right? So you're going to go a path all the way you can go first. Then once that path is explored, you go to the second path, which is this path. Does that make sense? So the next path next is E. And then finally the last branch, which is D, and C is already explored, so there is no point writing C here. C is already explored. Any questions? If somebody's speaking, I'm not hearing anything because I'm hearing like a buzzing sound, that's all. Let's look at the algorithm real quick. Okay, how we are going to implement all of this. Okay, both BFS and DFS, and then let's code as well. I'm going to explain BFS algorithm, then code it, then DFS algorithm, and then code it. So let's open let's say the previous problem. Okay, and let's just clear all of this. In this algorithm, let's talk about all the data structures that we're going to use. So BFS. Okay, for a BFS starting with graph and any vertex, let's say the vertex in this case is A. How are we going to run the BFS? So what BFS says is you explore a node, then all the neighbors of the node and neighbors of the neighbors of the node. So the first thing is we want to explore A. That means we need to process A. Let's say we print A. Processing means just the printing of the node at the moment. So we print A. Then we need to process the neighbors of A, which are B and D, right? And then the neighbors and the neighbors of those nodes. So we're going to call, we're going to do that B and D. Now it's one thing to say that since A is explored, we now need to look at B and D, but how do we actually do that? How do we remember that information? And the way to remember this information is through a Fifo queue. How this is done in a program is basically, how this is done in algorithms is that you have a Fifo queue. Just give me a second. Somebody had a question. All right. How this is done is basically you have a Fifo queue. So first, what you do is in the Fifo queue, first in first out queue, you put A, and then you process whatever the children of A are. So then basically you initialize a queue with the node A. Let's just clear this out. And right now, suppose this is the queue, like this. You add nodes from here and you remove from here. So whatever the node is to be processed, you put it in the queue, and then you look at that node. You pop from the queue and you look at it. You print A. Then you say, whatever are the children of A, put them in the queue so that they can be processed next. So B and D gets put in the queue. And the loop ends. Then you call whatever is the top of the queue, bring it. You bring B here. And then you say, whatever are the children of B, whatever are the neighbors of B, put them in queue. So the neighbor of B are right now what? D and E. Right? So D and E. Let's just put for now D and E like that. Don't worry about it. Okay. So D and E. And it's done after that. So what is the next item in the queue? D. Let's bring D up. What are the children of D? Let's put them in the queue. So you put like this, E here. So once you have this E here, there are no more children left. So this D is gone. Then you come to this D again. This next item is D. Where you pop it, but you see that D is already processed. So you don't need to take any action item on this one. And how do you see that this is already done? Is you have to keep track that what you have already processed. Okay, and you can do that by creating another data structure, which is a set. And you can call it seen or discovered. Some people call it discovered, some call it seen, doesn't matter. So here, whenever a node is done, you keep it here. That is, it is already processed. So when you encounter this D, you check whether it's already processed. If it's processed, nothing needs to be done. If it's not processed, then repeat this. Then you come to E. Is E in seen? No, not yet. So then put E here and put the neighbors of E in the queue. The neighbor is just F. So let's put F here. And then this is processed. Then you come to E again. Then you notice that E is already processed, nothing needs to be done. Then you come to F. Is F here in the queue? No. So let's put F here. And then what are the neighbors of F? C and Y. Let's NQ, C, and Y in the queue. And F is done. Let's put F here. The next node is C. Is C in this list? No. Let's put C here. What are the neighbors of C? None. Done. Let's put Y. Is Y in the scene? No, not yet. Let's put C here. And what are the neighbors of Y? X. Let's NQX. And the Y is done. Let's put Y here. And then finally X. Come X here. And no neighbors of X. And that's X is done and is seen. So at the end, when the queue is empty, when this whole queue is now empty, when the whole queue is now empty, there is a size equals 0. That means that you have processed the whole graph now. And you have done your BFS traversal. Any questions in this?
Himanshu, am I audible now?
What is that?
Am I audible now?
Yes.
Ah, cool, wonderful. My question is that would the weight of an edge decide whether one node is coming earlier to the second one? So let's say if the weight between A to B is 3, let's say for example, and the weight between A to D is 4, and we have to see which one comes first after A. So would weight be a deciding factor of making a queue?
It can be a policy decision. Yes. I mean, you can make that you can make the decision based on the problem.
Okay.
Yes. So currently, what I'm discussing is that there is no weight. It's it's just a all unit order. And the way I'm going to decide which one comes first is based on the adjacency list, whatever is first in the adjacency list. Okay. But you can choose to go in the adjacency list from the back as well. Doesn't matter. Essentially, this order right now doesn't matter. It can be whichever neighbors you want to pick, you can pick those neighbors. It will not matter right now.
I have a basic question.
Yeah.
So we have seen trees and graphs as data structures. So these queue and set are they different data structures as well?
So the sets are basically, the collection of distinct items. They are the built-in data structures that are given in every language. So the sets are those, and the Fifo Queue is basically just a. Sorry, 1 second. And the Fifo Queue is another simple array type of data structure in which items come from one end and then they go from the other end, maintaining the first in, first out order. And if you need more information, then there is a pre-recorded video of the Fifo Queue in my previous lectures, in which stacks, queues, and linked list.
Okay. Thank you. Okay.
Yeah.
And Himanshu, where can we find the old recordings?
I will talk about it after the lecture.
Sure.
How about that? Yeah. So now let's implement this. So what we're going to do is we're going to implement this, and then we're going to bring that code over again in this, and then compute the time and space complexity of this of that code. All right. So let's do that. So for that, what I'm going to do is I'm going to fire up my IDE. Just guys, give me a second. Let's bring it here. Just give me a second. My computer is acting a little erratically today. Okay, I'm just gonna save it as something like graphs.py. So let's begin with, first of all, representing the graph. And then we will write the code for the BFS. So our graph is something like this, right? So this is the situation. So what I'm going to do is, I'm just going to create certain variables real quick and name them in the form of those strings. So that it is easy for me to later on just call the variables variable names instead of using the quotes. So, and let's say y. Suppose this is the case. So this is A, B, C, D, E, F, X, Y. So there's nothing else here, right? Yeah, perfect. So I'm just going to use the variable names from now on. So I don't have to write these quoted strings every single time. So let's represent this graph. Suppose this graph is an adjacency matrix. All right, so let's go here and let's just say the first key is, let's say A, and the neighbors are represented as list. So what are the neighbors of A? Are B and D. Okay, so B and D. And then what are the neighbors of B? D, E. Then what are the neighbors of D? Is E. Then the neighbor of E is F. Then the neighbor of F is C and Y. So C and then Y. And then finally the neighbor of Y is X. Just making sure that we are not doing any mistake. A is going to be D, then B is going to D, E, D is going to E, E is going to F, F going to C and Y, and then Y going to X. Perfect. So that's our graph, an adjacency list. All right, currently everything is just a string. Now let's write the BFS on this. So what I'm going to do is I'm going to write a method. I'm going to use Python again. And what this does is that it takes two arguments, graph and a node, let's say V. And then we're going to call the BFS on this. So the first thing that we're going to do is we're going to create that queue that we need. So I'm just going to create a queue, which is nothing but a list. It's just a list. You're going to insert from one side and remove from the other side of that queue. Okay, so I'm going to put, let's say, V as the first element in the queue, because that's where our algorithm will begin. And then I'm going to create another set scene, which is a set, an empty set at the moment. That is, nothing has been explored so far. Now, how you write BFS is that you're going to iterate till this queue is empty. So you're going to write while queue, or you can write while the queue dot length is greater than 0. So while this queue is there, let's go back to this algorithm real quick. Where did it go? Yeah. We're going to remove an item from the queue. Okay. So let's say in this Python list, we are adding the elements from the 0th index and removing from the end. So I'm going to say queue.pop to get the item. This is the last item. So this is our current variable. So the current variable is q, whatever is the last item in the queue, just get it. So q.pop. Now we need to check whether the current is already processed or it's not processed. So we go here and we check whether the current is in scene or not. So we're going to say if current in scene, then essentially continue. That is, you don't need to do anything. Go back to this queue again. You have already popped the item, so the queue size is already reduced by 1. So you go to the next item of the queue and you pop it again. Otherwise, if this is not in scene right now, then let's say just print. Right now we're just printing. So you're going to say print current, and I'm just going to add a buffer so that we don't get a new line. So just print the current item and also add this to scene. So what we're saying, what we have said so far is that get the item from the queue, first item from the queue. Then if that first item is in scene, then you don't need to do anything. That is, we've already processed it. If it's not done, then just print the item and add that item to the set, which basically is the list of all the discovered items. So now, once this item is processed, we need to process its neighbors. My computer, okay. So what I'm going to say is I'm going to iterate over all the neighbors of the current. Okay, and what are all the neighbors of the current? So let's say if the current is right now E, then what is the neighbor of the current? They will be represented by graph of that node, right? The value for this particular key, E, right? So I can write graph current. So graph current will give me a list, and I'm going to say for all the neighbors in this graph, in this list, for example, let's say if this is A, then for all the neighbors in B and D, that is B and D. And we're going to do the same thing again. We can just say q.insert at the 0th position. It's add from the 0th position, the neighbor. And that's it. We can add a slide optimization as well. We can write here that if neighbor not in scene, then only add it. Otherwise, if it's already seen, then you don't need to really add this as well. And that's it. So this queue, when it's empty, it will give you the answer. Let's just run this real quick. Let's say BFS of graph, and let's say A, the vertex A. Let's run it. Let's see if this works. Okay, what happened? C. Key error C is not present. Okay, so I misrepresented the graph. Yeah, C is not present here. So we need to represent C as an empty list. That is, there are no neighbors for C. A, B, C, D, E, F, Y, and there is nothing for X as well. So let's add X as well. Empty. So those two are empty. Basically, there are no neighbors for those. Let's run this again. And we get an answer. A, B, D, E, F, C, Y, X, like that. Let's look at our code. C, A, B, D, E, F, C, Y, X, something like that. Yeah, same answer got printed. But let's run this code with our example so you guys can fully understand what I'm trying to do. Okay, and these are only three. There are only three main algorithms in graphs, so you guys can completely then familiarize yourself with it, and then we can continue. So let's do that. Let me just copy this piece of code here. Please give me a second. Let me just copy this. Let's go back really quick here. Let me just clear this. Just bear with me for a second. My computer is not helping me today. All right, come here. So that's our algorithm. So in this algorithm, suppose this is the graph and that's the vertex A, then this graph and vertex A get passed here. All right, they get passed here. So the first thing that we do is we create a queue. All right, so the first thing that we're going to do is we create a queue. And suppose this is our queue. And the first item that gets added to the queue is, let's say, A. Now I cannot keep on shuffling, so I'm just going to start from the back. Okay, suppose I'm going to say A. A gets added to the queue. And then I create a set as well. This is the set of the items that we have seen so far. And it is empty. Then I'm going to say while queue. That is, while the queue is not null or not empty, pop the queue. So when you pop the queue, A comes out of the queue. And there is nothing left here. And you see if current is in scene, then continue. But the current is not in scene, right? Scene is empty. Okay, so then print A. So we print the A here. All right. And then scene.add current. So we add A to the current. Then we say for neighbors in graph of current. So graph of current means graph of A right now will give the answer as B and D. So for neighbors in B and D, so let's say the first value picked up is B. If B not in scene, which is true, B is not in scene right now, then Q dot insert B neighbor. So we insert B now here. Similarly, we insert D here like that. All right, so that's the queue now. And then we go back to the beginning of the queue. While queue, the queue is not empty, it has two items, D and B. So then we say current queue.pop. So let's pop the queue and bring the current out, bring the B out. And now B is the current. So then we say if B is in scene, B is not in scene right now, then print B and add the B to the scene set. All right. And then for all the neighbors of B, what are all the neighbors of B? D and E here. For all the neighbors of B, which are D and E, if neighbor not in scene, insert them in the queue. They are not in scene, so then insert D and E like that. And then you move again to the top of the queue. So now you say, once again, pop the queue position. So then the next position that the item that comes out is again D. Is D in scene? No. So then add D here, add D here, and then bring all the neighbors in the queue. So you get the idea what I'm trying to do here.
One quick question.
Yeah, was it?
So when we insert at the 0th position, doesn't it mean we are inserting at the beginning of the queue, right?
Yes, yes. So
But,
this is the 0th index. So this is the, this is the 0th index, and this is the last index. Now, ideally, what I would do, so since I'm drawing, it will be very hard for me. Otherwise, it will be like this. So first B, then the next item comes is first. So first item is A. Then the next item that comes is B and D. So first B, and then D and B like that. So this is the 0th index. This is 1, 2, 3, 4, and like that. And
so
then
yeah, our question is generally when you do a queue, you just do insert. You don't say index because we assume that it always insert at the back of the queue, right?
So that is correct.
Is it not the case with Python?
So what you're saying is correct, completely correct. If we were saying queue, we will just say queue.enqueue, right?
Yeah.
However, remember that I have not created any queue data structure. This queue is just a variable name for a array.
Oh,
This is just a normal array.
got it.
Yeah.
Okay.
If I would have created a queue data structure with enqueue method, then I would not have to do all that. So, but essentially that's the algorithm. That's how it's working right now. Any questions in understanding this?
I have a question.
Yes.
So instead of using insert, can I use append?
So if you use append here, all right, you can use an append here. If you use an append here, then instead of doing this pop, so append, so suppose that this is the queue. Okay, suppose this is the queue right now. If you do an append, then it will add to the end. Then when you do the pop, it will remove the last element. So you have two options, right? So one is insert 0 and then pop here. Those are the two items, right?
Mm-hmm.
Or you can do append to add, but then when you do pop, you have to do pop 0. That means remove the first item of the queue.
Oh, I got what you mean. Yeah.
Yeah, so basically you have to maintain the first in, first out order in any way. Either you enter from the queue or you exit from the queue. When you enter from the queue, you are the first one to exit from the queue as well.
Yes, makes sense. Thank you.
Yeah.
I was a little confused thinking queue as a data structure earlier. So the only data structure used in here is the graph, right?
Yeah, the only thing is graph. This is just a list. If you notice, this is just a list. There's nothing here.
Okay.
Quick question there. The example that you provide in this case.
Yeah.
The example that you provide in this case for this and for this, will that make any difference in terms of time complexity?
No.
No.
It will not make a difference. Why it will not make a difference in terms of time and space complexity is this. That's a good question. Let me just first save this. Okay, now let me come here. Why it will not make a difference in time and space complexity is because suppose you have a Python list, okay, which is an array essentially, and this is the 0th index and this is the last index. You can call it n index, whatever. Right. Now, adding an item to the end of the list or removing the item from the end of the list is constant time, O1. But adding an item to the list at the beginning or removing the item from the list is O of n time. What is the reason? The reason is this, that suppose that the list is already arranged. Suppose this is your list, it is already arranged 1, 2, 3, like that. Now, if you want to insert, let's say, 25 in the first position, then essentially you will have to shuffle the whole list one position here, and then 25 will come here. Right? So insertion to the first position or to any position apart from the last position will be at O of n complexity. That is, n shuffles are needed to create that space. Similarly, when you want to remove the item from the first element, from the first place, let's say you want to remove that 1, essentially what that means is that 1 will be gone and then this array will look like this, and then everything has to be moved here, one offset. So that was once again n shuffles. So that will be O of n. So that O of n, if you want to add or remove item from the first index, and O of 1 if you want to do it from the last, because if you add from the last, nothing in this array from here to here is affected. Similarly, if you remove from the last, nothing is affected. In whatever implementation you use, okay, there are two approaches here. As I mentioned, you can insert on 0 and you can pop, or you can append at the last and pop from 0. This will be O1, this will be O1, this will be O of n, and this will be O of n. My mistake. Not this. This will be O of n. So one operation of either the inserting or removing will be O1 and the other will be On, regardless of the approach you used. So it will not change the time and space complexity in that case. Does that make sense?
Yes, thank you.
Okay. Now I have a question for you guys. What is the time and space complexity of this code actually? What is the time complexity of this code?
Is it O of n plus 1?
On plus 1. What is n here?
The list or your queue.
Okay. So in the graph, in the world of graph, what happens is for any given graph, you have some number of vertices and some number of edges. And you discuss the time complexity in terms of these guys. So you will say, let's say OV or OE or OV plus E, like that. Okay, so let's say if a graph has V vertices and E edges, then what would be the time complexity of this? Both the things are important. Both the things are important because if you see the algorithm, let's look at the algorithm real quick. This queue here is iterating on the vertices, right? For all the vertices, this queue is going to be the queue will have a size relatable to the number of vertices. Whereas this loop here is going to all the neighbors for a node. So this is going to be all the edges that for all the nodes in the queue, this will iterate over all the neighbors of those elements. Right? So if there are V vertices and E edges, what is the time and space complexity of this code? What I'm going to do is I'm going to give this as an assignment. All right. This is the algorithm. I'm going to post this code as well. You think about it and tell me. And you can write your explanations. Right. And if you have any difficulty, let me cover some basic material here real quick.